We've been dealing a lot with the mean value theorem lately and doing some proof type problems, and you learned even more about the mean value theorem earlier, and even earlier than that, we learned about linear approximations. And you might have had this question like, hey, well, these guys can look pretty similar. What's the difference between them? How are they similar? How are they different? And maybe you haven't had that question. Maybe you're like, what? These guys are similar? How? And in this video, I want to clearly tell you, I want to clearly kind of go through, okay, what are some similarities and differences between these two guys? What are they saying? What are they not saying? And make that pretty clear. So let's first try to get this linear approximation formula to look like our mean value theorem. And maybe before we start, I mean, what do we have written out here? Here's the mean value theorem. You've seen this before. Here are all the qualifications to use the mean value theorem. This is written out. And on this right-hand side, we have a linear approximation, and it's for some x near some x naught value. And again, this is just creating a tangent line. This is creating a tangent line for our function, and we use that tangent line to approximate values of our function. That's all the linear approximation is. If you haven't seen those videos, I would go and check those out. But we said we want to compare these guys. So first, let's just show you that this guy over here, this linear approximation formula, can end up looking pretty similar to the mean value theorem. And here's how we're going to do that. Let's subtract over f of x naught, and we have f of x minus f of x naught. And this is approximately equal to f prime of x naught times x minus x naught. All right, now let's divide both sides by x minus x naught. So we have f of x minus f of x naught over, let me get that straight. Here we go. Over x minus x naught. And this is approximately equal to f prime of x naught. So you can see we're getting pretty similar. Now, what we're going to do is going to let x be equal to b and x naught be equal to a. So we have this. We have for some b near a, we have f of b minus f of a over b minus a is approximately equal to f prime of a. All right, now you can see, whoa, these guys are looking similar fast, and they are. So let's just get a few more notation bits out of the way. So we're going to let b minus a be equal to delta x, so change it x. And then f of b minus f of a, we're going to let equal to a change in f, so delta f. So we have this. Rewriting the mean value theorem, we have delta f over delta x is equal to f prime of c. And again, that c is on our interval. All right. And then linear approximation is this. Under that notation, we have delta f over delta x is approximately equal to f prime of a. All right. So these guys, you can see, are looking pretty similar. So what are these guys saying? How are they similar? How are they different? Let's talk about that. Well, you can notice on the left-hand side, we have delta f over delta x in both of these. So if you want to compare that to speed, and I think that's the best way to talk about these things, at least in my brain, to talk about speed. So this is saying, this mean value theorem, and again, we've already really talked about this a ton. This is saying that for our time interval, if you're thinking about a car going on a trip here, that the average speed that you have for that trip, that you're guaranteed to be going at least one time over that trip, that same average speed. So at one time, if you're for a trip, if your average speed is 60 miles per hour for a car trip, at one time during that trip, you're going to be going 60 miles per hour. You're guaranteed to be going at least one time 60 miles per hour. That's what the mean value theorem is saying. And now the linear approximation also has an average speed here. But again, a linear approximation is used on a smaller interval here. The larger we try to go beyond where we based our approximation to use it, the less accurate that we can be with it, really. So this is for a smaller interval, and it's saying that our average speed is approximately our initial speed. And again, if I were to explain that out to you, it'd be kind of, again, you could take a car trip. If you were to track your speed going on a highway, right? Let's say you're going 60 miles per hour on a highway, and you were to, okay, I'm going to track my speed for the next 3 seconds, and barring nothing horrible happens, you don't get in an accident or something, that'd be horrible. let's just say you're driving normally for that 3 seconds and you're going 60 miles per hour on a 60 mile per hour road and you're just driving. Well, your speed's going to barely fluctuate, over those 3 seconds. So this is saying that over those 3 seconds, your average speed is going to be approximately equal to the initial speed that you entered that 3-second time interval where you were tracking your speed. And I guess I can continue. Let's continue to unfold this. I want to continue to explain this. So this is how you've seen the mean value theorem. Another thing that we could extend off of this is more of an obvious fact. It's this, that we could say that this average speed is in between our minimum and maximum instantaneous rates of change, instantaneous speed. So this average speed's in between our minimum and maximum speed. And you're like, oh, that's duh. Well, you could see this in a textbook. So maximum f prime of x, and that's for our full interval. That's for our full interval. And we have minimum f prime of x over our full interval. And again, this is some mathy notation, but what is it really saying? Well, if we relate it to speed, this is saying that our average speed is in between our maximum speed and our minimum speed. That is all this guy is saying up here. Our minimum speed. Okay. So that's what this is saying. And again, let's get some graphs going. I think talking about these guys with some graphs might help us out. So graphs. Let's do some graphs. Let's do some graphing. So here we go. Let's do a distance versus time graph, and let's keep our analogy of talking about a car trip. So maybe you're going on a trip, something like that, and we were to look at a time interval from A to B. All right. And what you've seen so far with the mean value theorem, this should be more review from earlier, is when we construct this secant line, the slope of this secant line, we are guaranteed some c value in which we're going to have the same slope when we make a tangent line there. So again, I guess with our example, if your trip between this time A and B, if your average speed is 60 miles per hour, you're guaranteed to be going at least some point in this time interval 60 miles per hour. And it looks like it's going to be right there. Right there. So that could be your C value. So that's what you've already seen with the mean value theorem. And the only thing that I've added on is really an obvious fact, and I want you to see that your average speed is going to be in between your minimum and maximum speed. So if we were to look at that graphically, we're going to look for kind of points that have the steepest slope and the shallowest slope. So let's do that. We'll put our minimum speed, and we are in purple, and we'll look for the shallowest slope. And to me, that looks like it's somewhere over here. Somewhere over here, okay? And then our maximum speed, we'll put that in, I want that in blue. Put that in blue. And we're looking for the steepest slope and on our interval, and that looks like it's somewhere right in there. So again, this up here is just saying the following. If we were to compare our slopes, here's our maximum speed and our average speed, somewhere right in there, okay? Our average speed's in between our minimum and maximum speed. We'll throw in our minimum speed. So that is all the above is saying. Now, how does this compare with linear approximations? Well, let's get a graph for that going. So again, a distance versus time graph. Here's our car going on a trip, something like that. And again, we want to take smaller intervals with a linear approximation. So we're looking at a smaller interval here from A to B, okay? And what this is saying here is that our average speed is approximately equal to our initial speed. So our average speed is approximately equal to our, I forgot to write speed. Average speed is approximately equal to our initial speed. And what does that look like graphically? Well, graphically, again, we're going to make a secant line right here. And the slope of that secant line we're saying is approximately equal to the slope of our tangent line at when we construct it for this time at t is equal to a for our function here. So if we were to give a tangent line here, you could see that our slope of this tangent line at some time a here, our speed, is going to be approximately equal to our average speed. And you could see that graphically. So we have that here, and we can finish this off like that. approximately equal to the slope of this tangent line here. So again, they're saying some similar things. They look pretty similar. They have some similar components to them, but graphically they're saying and just colloquially they're saying a little different things. So our average speed's in between our minimum and maximum speed for the mean value theorem, and our linear approximation, we're saying that our average speed is approximately our initial speed. So hopefully that can clear up some things, especially when you see the mean value theorem and the linear approximation formula presented like this. And you're like, whoa, those guys are looking similar. How are they different? Hopefully that cleared things up for you a little bit graphically and using some examples of talking about cars and speeds. And in the next video, we're actually going to use this extended form of the mean value theorem. In order to solve a new type of problem.